So to start off, let's introduce ourselves. So I'm Bobby,
I'm Simran.
I'm Ashka.
and our fourth instructor Gung will be joining us at about 9 when we have our intermission break. And we're here because of two reasons. One, because we love to teach, and two, because interviews can be really, really frustrating. Like, you have to learn an entirely separate set of skills from what you're going to be doing day to day in your everyday software engineering job. And it's just really, really annoying that you have to spend hours upon hours to sort of get the knack of interviewing and then not use that information at all, pretty much. So, having gone through this process ourselves, we thought that it would be really nice for us to try to share some of the nuggets of our knowledge that we've accumulated throughout the course of these years. So, that is basically what this course is going to be for this year. So what exactly are we going to be covering then? We have 3 core units. So we're going to start off with basics. That is strings, arrays, hashing, binary search, and big O. After we have a grasp of the basics, we're going to move on to data structures. These are the linked lists, stacks, queues, trees, and graphs that you learned about in CompSci 201. Then, once you feel comfortable enough with that, after spring break, we're going to move into algorithms. And these are going to be the stuff that you mostly learn in CompSci 330. Divide and conquer algorithms, greedy algorithms, recursion and backtracking, dynamic programming, that sort of stuff. So I know that I threw out a lot of terms at you, but don't worry, we're going to go over all of them very, very slowly, covering about 1 per week. Here's how we're going to teach you here's how we're going to be teaching you, right? So the first is we're going to lecture. That's what I'm doing right now. We're going to hear an introduction of a concept and watch us do a mock interview of that concept. If you're feeling particularly brave, we also take audience interaction. After that, we have practice interviews as well. That is where you pair up and take turns giving each other mock technical interviews. These happen at the end of every single one of the past 3 units, the basics, the data structures, and the algorithms. Finally, we have coding competitions, and we use the open source Caddis platform in order to do this. Caddis basically is like an online judge. I don't know if y'all have ever used, if y'all competed in ACM ICPC, or whether y'all have used HackerRank or something like that. But basically, you submit your code and it spits out whether or not you were able to do things right. Or actually, that's how you judge APTs in CompSci 201. I forgot. Yeah. It's basically like a CompSci 201 judge, except that you can form teams with it, and you also get points based off of how quickly you solve it and at what % you get right. So it's really, really cool. It's an amazing open source platform, and I think that it's a great way for you to both hone your coding skills and get to know some of the other people in this room a bit better throughout the course of this semester. So this class meets every Tuesday from 8 to 10 p.m. Search Cycle 136. That's this room, this time. This is with one exception during spring break, but that's kind of obvious. We run until the week right before LDoc, because no one's going to come to something on Tuesday night before LDoc. But it is a decent, we do cover a decent amount of material. That's why we do meet every week for 2 hours. Keep in mind, this is also sort of a drop-in, drop-out course. While it does make sense for you, while you will benefit from coming consistently to class, if you feel very comfortable with certain aspects of this class, then you could just choose to not come to parts of it. For example, if you are a god at linked lists, then you could choose to not come to the lecture in 4 weeks. We do recommend that you come consistently, though. So this is a bit of a stickler, right? So are you ready to take this class? There are no hard requirements for you to take this class. As long as you're able to code in something of your choice, you could theoretically be set for this class. However, it might make this class a lot easier if you have some advanced CS classes. And by advanced, I mean just something beyond CompSci 101, right? So if you have 201 level knowledge of basic data structures like strings and arrays and hash tables, linked list trees, and graphs, that will help you a lot in the second third of this unit in which we go over those data structures. Because the way that's going to work is we're going to spend a little bit of time reviewing exactly what those data structures are and what their properties are, but the meat of the time is going to be spent actually coding. So having that previous knowledge does help a lot. Again, like I said before, you should have some familiarity with Python or Java, because that's what most of our examples are going to be done in. And you probably should bring your laptop to class just for those programming challenges, and also because a lot of y'all might want to code along as someone codes along on the screen. Emails will be sent out before class every week regarding what prior knowledge is helpful. If you didn't comment on one of the posts inside the 2021, 2020, or 2019 groups, or the Duke CompSci group, then make sure that you leave your net ID with me afterwards, so that way I can make sure that you get the email telling you what you need to be prepared before you go to that week's class. All right, so a bit more detail about what I mean by basics, data structures, and then algorithms. So this week, the first week, we're going to be covering the fundamentals of this class, like just logistical things, and then big O and binary search. Week after that, it's going to be strings, array, and hashing. After that, we're going to have our first practice interview and coding competition. I already sort of went over exactly like what those things mean. And just as a quick preview, this is about what we're going to be going at the rate for data structures. Keep in mind, all of these slides are posted on the course website. Y'all all know about the course website, right? Yes? If anybody doesn't know about the course website, it was sent out in the email. It's just docatalyst.co/interview prep. And once you go there, like you'll both be able to look at this calendar and also have PDF versions of these slides. Keep in mind, they might be somewhat different because like we're all just busy Duke students, and some of us will be making changes to the slides up till the very last minute. But for the most part, those slides will be consistent between what you have on the website and what I'm showing, or what the other instructors will be showing during class. So the last part of it is algorithm. This is the most tentative just because I don't know exactly how fast this course is going to run, but this is hopefully what we will be able to cover. And this TBD most likely will just be going over the hardest problems that you'll had a bit most issues with actually completing. And just as a fun thing, on the very final day, we're going to be ordering pizza again, and we're going to we're going to have a pizza party while we do this long coding, while we do this coding challenge. So a couple of things about what we don't do, right? There's only so much that you can cover when you meet once a week for 2 hours, and that's why we don't cover a lot of stuff that actually is in 201, and we also don't cover most of the stuff that's in 330. So we don't cover advanced data structures. Y'all might have heard of this from 201, like tries, union finds, self-balancing trees, like the red-black trees or AVLs or whatnot, mainly because you don't see them that often in interviews. In addition to that, we won't be going over advanced runtime analysis, such as master theorem, immortized analysis, that sort of stuff, because you will mostly ever only be asked to analyze the runtimes of code that you write. And if you're writing something that requires that advanced of runtime analysis, you might be doing something wrong. We also won't be doing advanced graph-related things, such as best first search or Dijkstra's, network flows, minimum spanning tree, that sort of stuff. Also because we just don't see those things that often. Finally, and most importantly, we are not rigorous. We are not a computer science course. We are an interview prep course. We will say things without proof, and we will just hope that you believe us. But the things that we say are generally true. I will make caveats for when things are not entirely true, because otherwise I don't want to confuse you when you do go into your, that way you don't get confused when you do go into your 230 or 330 further classes. So, quick poll, just show of hands right here. How many of, so most of the instructors are most familiar in Python and Java. I want to know what y'all would prefer for us to do the interviews problems in. Just because, there are benefits and drawbacks of both. I also just don't know, the general spread of the room as to what your general familiarity is with Python versus Java. So, show of hands, who would prefer Python? Okay, we got one. All right, who prefer Java? Great, because I haven't written Python in years. Okay. Python is a language that does have its benefits. It tends to be less verbose. But I think that most of y'all come into Duke with AP Comp Sci and then Comp Sci 201 experience, and those are both in Java, so I guess I sort of expected that a little bit. All right, cool. I think we're done with the fundamentals at this point, so let's jump into our first topic, which is big O complexity. All right, so just show of hands, who has taken Comp Sci 201 in this room? Great. Who's taking Comp Sci 330? Okay, you're in it right now. Awesome. So, cool. For most of y'all, this should be a review, but we will try to go slowly for those of us who haven't gone through the entirety of 201 yet. So the fundamental question that big O or asymptotic complexity asks is, if I increase the size of the input n times, how does the runtime or required space change proportionally? And some common ones that you're going to see are n or n squared, n cubed, log n, 2 to the n, n factorial, or just it doesn't change at all. Now, this is not the computer science definition of big O. that's closer to, what we're talking about is closer to something in computer science called big theta, but for the purposes of interviews, we're going to call this big O, and everybody else in the industry is going to call this big O. So here are a list of common time complexities. And these time complexities are things that you should sort of have in the back of your mind, because I think that for a lot of people, having a concrete example of certain time complexities is really, really going to help, right? So at your fastest operations, your constant time, or O of 1 operations, you have these arithmetic operations, which includes comparison between numbers. That is your divide, your mod, your addition, subtraction, your bit operations. And this also includes accessing memory or getting an entry from a hash map. So at a bit higher up, we have O of log n. And I think the most common time that you're going to see this is probably when you're coding some form of binary search. With O of n, it's something where you have to hit every single element of an array, or just a single for loop. With n log n, this is something that y'all will see very commonly when it comes to sorting or other divide and conquer algorithms. This is the minimum bound in sorting, so you cannot sort in faster than n log n. If you're ever asked something with regard to sorting, just think n log n. And then you have the n cubed, n squared, whatnot. Most of these times you're going to see it when you have a double or a triple or quadruple or whatever nested for loop. And then finally, we have the really, really slow algorithms, the factorial or the exponential time algorithms. And most of the time, you're going to see these when you're trying to brute force every single possible combination. Most of the time, you won't have to look at things that have those last runtimes unless you're doing something like enumerating all possible solutions or doing something with recursive backtracking. But when we'll get there, we'll talk about it. For now, I don't think you need to worry about it too much. Yeah.
So actually, what I found really helpful for remembering kind of relative complexities was this website called Big O Cheat Sheet. And so they have especially in the beginning, they have a little chart here, and it shows in color what are the best runtimes, so you can visually map it, because you obviously know what these functions look like. Maybe it's easy to get mixed up in the moment. So, and then if you scroll down, they have each data structure and each operation you can do and what their time complexity is. So it's kind of a good study guide. And then if you scroll more, there's array sorting algorithms and their time complexities. So that would be helpful too.
Yeah, there are a ton of resources for remembering time complexities, probably more so than any other topic. So definitely the internet is your friend here. Thanks, Ashka. Now let's talk a little bit about Big O concepts. So when you're given something that's not just a very classic computer science algorithm, how are you going to find the Big O of that? So first you need to remember that only the biggest term matters, right? So for example, if you have n to the fourth plus 10,000 times n cubed, then the second term dominates for small n under 100. But at n equals 1 million, the first term will outweigh the second term by 100 million. So, like I said before, Big O is also known as asymptotic time complexity, or asymptotic analysis. And that means that you're going to want to think about things as n tends towards infinity. At those sizes, it's only the biggest term that will matter. The second really important concept is that nesting multiplies Big O's together. For example, doing a binary search for each element of an n-element array will take n times log n operations, so it's O of n log n. This is also the same reason why when you have double or triple nested for loops, it's going to be O of n squared or O of n cubed, respectively. The last issue is that you should drop the constants in front of your terms. Like I said before, Big O only matters when n is really, really big. At that point, any constant, no matter how big or small, it just doesn't matter. So that's why those two things at the very bottom are both still O of n. All right, so I don't know if you'll have the slides downloaded. If you do, I would encourage you not to look at the slides for now because those have all the answers on the right. So let's just go through these three functions, right? You have sum1, sum2, and sum3. So let's just first think about what the time complexity of sum1 is. Would anybody like to venture a guess? Yeah? O of n? Why? Yeah, it's a for loop that goes through every single element of the array. But importantly, you need to remember that the operation inside that for loop is an O of 1 arithmetic operation. If we did something that was not O of 1, then it would be O of n times whatever other thing. So what about sum 2 then? Yeah, Simran.
Quick question: Can all of you guys see, or is there a glare? Are you good?
So
Can you still see? Or...
yeah,
We tried.
let's try to. Okay, all right. Is that better? Wow, is the lighting still like? It's pretty good.
Do you want it to see the slides?
No, it's good. We're recording the screen, so yeah. All right, awesome. So sum 2. What do we think?
N squared.
Yeah, n squared, right? Why?
Because it's nested, 2 nested 4.
Yeah, it's 2 nested for loops, but most importantly, what you're doing on the very inside right there is still O of 1. So that's why you have O of n squared. What about sum 3? Yeah, it's O of 1. Why? Yeah, you're just doing a series of arithmetic operations. And, like, that is why, even though all 3 of these functions calculate the exact same thing, which is the sum of the first n minus 1 numbers, they still have very different runtime complexities. So let's look at something a little bit harder. So what about so I've copied the code for sum 1 up there. What do we think the runtime for loop sum is? Any takers? Yeah. Yeah, O of n squared. Why? Yeah, so this is what I was talking about before. Even though you're only going through like n elements technically, you're still doing an O of n operation every single time inside. So you multiply those complexities together. What about triple sum?
Oh, 3.
Any takers? Can you repeat what you said?
Oh, 3.
O of 3n. Okay. So yeah, right. So you drop the constant like right in front of it. So like O of 3n, it's also technically correct, but like you should drop the constant and just say O of n. So it's O of n because you see that you're only doing sum 1 a total of 3 times. So that's only going to take O of n time to complete. What about no sum? I feel like the title might give it away a little bit.
O 0.
Yeah, it's constant time. Why?
The loop doesn't run.
Yeah, the loop never runs. You initialize a variable and you return the variable, and that's it. So that's constant time. I think that the key lesson to learn from this is that big O concepts can start off like really simple. You can distill it down to just a few central rules, but you should really, really be careful because just by changing like the bounds of like this iteration, you can also completely change what the big O time complexities are. So make sure that even if you feel like you immediately know the big O of something, make sure that you take some time and still really, really think about how many, like really, really think about what the code is doing as opposed to what you think the code might be doing. All right, so let's talk a little bit about challenge sum. So challenge sum uses both sum 3 and sum 2 as function calls inside of it. So what do we think that the runtime of challenge sum is going to be? Yeah. Why do you think it's n to the 4th?
So if you look at sum 2, the runtime is n squared, as you saw earlier, and then sum 3 returns a value that's roughly n squared, and so the loop runs n squared times, and the function within the loop has a runtime of n squared.
Yeah, that's perfect. I think that it's really important to know that like Big O doesn't just talk about like space or time complexity. Big O is talking about like just functions in general, right? So even though sum 3 runs in O of 1 time, the return value of sum 3 is like O of n squared. It's about n squared, right? As n tends to infinity. And just like, what was your name?
Dorian?
Yeah, just like Dorian said, that's why you have to run through that outer loop n squared times and do n squared work every single time you go through on the inside. Multiply those together and you get O of n to the fourth. Usually, things don't get this hard in terms of big O complexity inside interviews, so don't worry too much about something that's like at this level. So, just a couple of reminders about big O. First, you should know the difference between average and worst case runtime and what conditions will cause those times. So Oshka's resource, the Big O cheat sheet, is very, very helpful in this because they will also give you like best, worst, and average case runtimes. So for those of y'all who took 201, you'll know that quicksort is O of n log n average case, but it's O of n squared in the worst case. And those can be like very, very different. And to be fair, those only happen under very specific circumstances, but like sometimes interviewers do like to quiz you on tricky things like that. Just a side note, it is not the same thing as the difference between big omega and big O. We don't have time to explain what that difference is, but average and worst case runtime do not refer to big omega and big O. Those are two entirely different concepts. The second is that, like, because Big O does talk about functions, you should probably remember some basic logarithm and series rules. There's two that I found to be particularly useful. The first one is that the log base b of n is equal to O of log n for any base b that's greater than 1. And you can prove that using, like, basic log rules. That's why a lot of times you'll see, like, log base 2 of n or whatever dropped to be, like, O of log n, because those things just are the same. And the second one is that the sum of a geometric series is finite. This will come in more useful when we talk about divide and conquer algorithms after spring break, but this does come in relatively useful. So the last one is that you should know what you're doing big O in relation to, right? So for all of the previous examples that we had one input and that was just like an int n. But in most cases, you're going to have like something where there's more than just like one input or more than one thing that you can like compare yourself to. So for example, an algorithm which sums together every element of an m by n matrix is O of A if A is the total number of elements of the matrix. But if you consider like a matrix of an m by n matrix, then it's O of mn if you talk about the number of rows and columns themselves. So be very careful that you're very specific about like the variables that you use when you are talking about big O. So to hammer that point home, let's talk about these two problems. What is the big O of product 1? Yeah. Why is it O of B? Yep. And similarly, what do we think about product 2? Yeah, O of A. For the exact same reason, right? For product 2, the for loop goes through A times. And everything that you're doing on the inside is an O of 1 operation. Alright, cool. So, let's talk about something that might be a little bit more difficult. So, what is the runtime of this? To be fair, if you haven't seen binary search before, this might be a bit hard to analyze. But considering that our next big topic is binary search, I think it would be a nice segue to talk about binary search's runtime right now. So this might be something that like you just memorized at this point, but what's the runtime? Yeah, O of log n. How would you, in your own words, say why it's O of log n?
Well, every time you recurse through, you always divide what you're looking at by 2.
Mm-hmm. Okay, and more specifically, what does n stand for in this case?
The number of nodes in the tree or elements that are in.
Yeah, it's the number of elements in the array. So importantly, like there's some problems in which like your algorithm might be like O of n, where n is the largest element in the array or something like that. So just be very, very specific when you're talking about that. And you can also simplify this using those log rules. We're going to speed a bit through this part, but if you want to come back to it, you can always review the lecture notes later. So everything that we talked about there was about iterative runtimes. What about recursive runtimes? So in a lot of cases, like you will write a function. So every function that can be written iteratively can also be written recursively. That's like one of the fundamental tenets of like computer science in general. But there's a lot of functions which can be written a lot more easily iteratively or a lot more easily recursively, which means that you will have to run into recursive runtimes at some point in your interviewing time. So I would separate this into two main cases, one of which in which there's only a single recursive call per main call, and the other in which there's multiple recursive calls. So multiple recursive calls get a little bit hairy, and we'll talk about that in just a bit. But for now, let's talk about what if there's only one single recursive call. In that case, you just need to think of two things. One is how much work is being done in the non-recursive part of the function, and the second is how many recursive calls it takes to get to your base case. So your total work is just the product of those two. I think this might be a bit abstract, so let's talk through a couple of examples. So let's talk about power. And first of all, someone just tell me what exactly this function does. Yeah.
Raises a to the power of b.
Yeah, it raises a to the power of b. What is the runtime of power? I'll give you all a second to think about it. This might be one of the cases where, like, you might want to like bring out pencil and paper, huh?
Is it O of B?
Is it O of B? Why do you think it's O of B?
So whatever B is, you're basically going to call this function for B, then B minus 1, then B minus 2, all the way down to 0. So essentially, you're calling this function B times, and everything in the function looks like it's constant.
Exactly. That's perfect. The problem size shrinks by 1 each time, just like you said, and so we're going to reach the base case in B calls. So what about mod? Oh, what about mod? Yeah. O of 1. Why do you say it's O of 1?
So it's not recursively calling anything, and then all the operations inside there.
Yeah, it's tricky. You would think that it's a recursive function, right? Because I was just talking about recursive runtimes, but be super careful. Be super, super careful. I just changed like one line basically, but like it completely changes the runtime because it never enters a recursion at all. So awesome. So here's some code that calculates the Fibonacci numbers. And we call this multiple recursive calls because if you'll notice in every previous example, there was only like one recursive call here, for example, right? And in contrast, over here, we have 2 recursive calls for every regular call of the function. This makes things a lot harder because instead of having to worry about like just, a linear decrease of like, your recursive call stack, all of a sudden you might have something that ends up spreading out and looking a lot more like a tree. However, there are a couple of things that you can like keep in mind, and for the most part, these should be good enough to get you through interviews. So the first rule is that if the input size decreases linearly, then the runtime is O of f times x to the d power. And this seems very technical, but it's actually very intuitive once you think about it. So x is the number of subcalls per function call, and f is the number of non-recursive work done per call, and d is the number of calls needed to hit the base case, aka the depth of the recursion tree. And why is this sort of intuitive, right? Because this is super similar to what we had before. The only difference is that instead of it simply being the non-recursive work done times d, now because we have a possible branching, you have to take x to the d power where x is the number of subcalls. This tree that I was talking about can be seen over here. And just like before, what you can sort of see is, just like before, you can sort of take any individual leg down to the bottom, and that would be your regular, like, single recursive call runtime. But because it's splitting in half approximately twice every single time, or it's splitting into approximately 2 problems every single time, you have to take 2 to the d power. So that's why at the very end of it, you see that this implementation of Fibonacci takes 2 to the n time to run, where n is like the nth Fibonacci number that you want to calculate. Okay, so the second rule is that if your function size increases by the inverse of the amount of recursive calls, then the runtime is O of f of n times log n. So just like before, So the difference is, over here, we said that F was the number of non-recursive work done per call. Over here, we say that F is the number of work done per level. And these levels are the ones denoted by dotted lines over here. And N is the total problem size. So an example of this can be merge sort, right? So the input size, so merge sort works by basically like recursing until you get to subarrays of length 1, and then merging these sorted arrays one by one. So your problem size decreases by a factor of 2 at each level, but each call to merge sort also has 2 recursive calls. Therefore, you can sort of think of these two as canceling out. And you can sort of think of this as the area of a rectangle, right? So over here, you have N. That's like your N element array or whatever it is that you're working on. And you're going to stop at a point where your subproblem hits a base case. And for merge sort, that's going to be when you hit like log N. That's when you hit the depth of this tree. So if you take the area of this, then it'll end up being N times log N. If you had something that, like, for example, where here was like N squared or N cubed, and here was log N, then same math. You would just calculate the area of that rectangle, so to speak. There's a lot of caveats to what I just said, because those are two very, very specific examples. So the first one is to always remember, if you have multiple recursive calls, it's an entirely different beast than single recursive calls. If your recursion diagram looks like a linked list, like just linear and not a tree, then don't try to use the rules on the previous 2 slides. You'll get something horribly wrong. So the second caveat is that this is an advanced topic. It's actually the first topic covered in CompSci 330. So if you really want to know how these recursive runtimes work, then you should probably read up on master theorem at some point, which covers another small subset of recursive runtimes, because recursive runtimes just tend to be really, really complex. An example of how I am wrong is that this example that we had over here for Fibonacci is not actually O of 2 to the n. There's a tighter bound of like O to the 6.18 to the n, where it's like the golden ratio to the n. So the final thing is memoization can often work best here. We'll get to exactly what memoization is when we hit recursion in the third part of this lecture series, but you will rarely be asked to write a recursive function with the multiple calls that you've never seen before. Some of y'all might be asked to write Fibonacci at some point in your life, but you have probably seen Fibonacci several times at this point, and there are a lot of methods to speed up your stuff such that it doesn't take like an exponential runtime like you see in some of these cases. Now let's talk a little bit about space complexity. So we spent all this time talking about time complexity, and for the most part, people will only ask you about time complexity. But in computer science, there's often trade-offs, and in a lot of cases, you can like speed up your time complexity a little bit by increasing your space complexity. And we're going to talk a little bit more about that next week with hashing. So basically, space complexity does get asked sometimes, but not nearly as often. And another reason why is because it tends to be a lot simpler to reason about. In iterative cases, just think about like space complexity as like the extra space. How many things you're stuffing in a hash map or in a memoization array or stuff like that, versus like how much stuff you're given as input. The second rule to remember about space complexity is that you don't include the size of your input in space complexity. So an example of this is bubble sort, right? You'll remember this from like CompSci 101. Bubble sort was just the one where you like iteratively compare like 2 successive values such that the larger values quote unquote bubble to the top. That's done with only a couple of extra variables and no extra array or anything like that. We don't say that bubble sort is O of n because it's working on an O of n array, because that array is where you're inputted in the first place. So don't include your input variables in space complexity. However, you should include call stack space. What's call stack space? Well, every recursive call needs to have some sort of marker such that the function can like remember what was calling it beforehand. And you might learn more about this if you've taken like CompSci 250 or like OS or stuff like that. But point being, whenever you make a recursive call, you always take up some like some space inside that call stack. And if you've ever like written a bad recursive function where like you might have seen like Java lang error stack overflow or something like that, yeah, that's what it's talking about, because every single recursive call does take extra space. The total amount of extra space is just the max like recursive call depth. So something that's important to know about this is, or an important example is quicksort, right? So quicksort also doesn't use an auxiliary array, but because it's a recursive function and it has an average call depth of O of log n, its extra space is O of log n average case. That is if you write a recursive quicksort. So, caveat, what does constant really mean, right? Someone, we said before, had an O of n runtime, yeah, because like, you know, you have this outer thing that goes through n times, and every single time you do O of 1 work on the inside. But Java has a maximum size for integers, right? So theoretically, you could say, yeah, well, everything's going to only run up to like a certain maximum bounded size, so it's really O of 1. But most interviewers aren't going to consider this O of 1 because that constant's like 4 billion. So normally you wouldn't say that this is O of 1 runtime, even though you technically could say it depending on what language you're doing it in. So why did I bring this up? This sounds stupid, right? But this becomes really important when you're talking about space complexity. So for example, say that you're storing like a hash map of like how many times each character shows up in a string, and your interviewer says that your input is an ASCII string. So there's only 256 different ASCII characters. That means that you could use like an int array, 256 long, where like every element of that array references like how many times that character showed up, and that's just O of 1 extra space complexity. So when it comes to space complexity, think a lot more about like what constant really means. All right, that was a lot to think about. Let's take a break and come back in 10 minutes, and then we're going to begin binary search at that point. So, side note, if I'm going too fast, like, you can literally just say, like, yo, can you, like, re-explain that? We will have a anonymous feedback form on the website up sometime in the next couple of days. This is the first time that we're teaching the course, so we hope that y'all will have some like constructive feedback that we can improve on. Because at the end of the day, like we really want this just to help y'all. Awesome. Let's start again at like. Actually, let's take 15 minutes. Let's start at 9. Welcome back, everyone. What we're gonna do now is we're just gonna like go over a slide that sort of reviews everything that went on with like these big ideas, right? So if there's 6 takeaways that you have for Big O, like these would be it. The first is to memorize your O of 1 operations because they're the base of every function. This is like memory access, like hash set access, math, comparisons, bit manipulation. Just remember them so that way you don't get confused about it. The second is that like you should have your basic concepts down, right? About how you ignore the constants, you look at the biggest term, and how you multiply nested complexities. Then we talked about multiple variables, about how like you should be like in the clear in terms of defining like what n means in O of n. And then we talked about single and multiple recursion and how those have extremely different runtimes. But how you can generalize multiple recursion to usually being something that's like exponential or something that's like n log n. And finally, we talked about space complexity, where it was a lot simpler, where all you have to include is just extra variables being declared and the number of recursive calls implicitly being run. You don't include the input variables themselves. So if you ever need to like come back to this, I think this slide might be very nice when we're talking about runtimes for the rest of the semester, because for every single problem that we do from now on, we will ask the space and the time complexities. So let's move on then to binary search. All right. So binary search is something that like has like a really technical name, but for most of us comes like relatively intuitively, right? So actually let's get some helpers for this. Simran and Ashki, can you come up? Okay. All right. So Ashki, can you go over to that side, and Simran come to this side.
Okay.
Okay. All right. Cool. So Ashka, her name starts. Wait. What? Hold on. Okay, Simran starts at Simran represents the beginning of like an old school like dictionary, right? Like a printed out dictionary. And Ashka represents the end of a printed out dictionary, and I represent the word catalyst, which is somewhere unknown in the middle of the dictionary. Say that you're like a little kid and you don't know what the definition of catalyst is. A really slow way of finding that definition is to like go through from the very beginning and flip through every single page until you get to the CAs, and then you're like, oh, catalyst is there. But there's probably a lot more intuitive method that you learn like sometime throughout your schooling. And that's to flip to the middle of the dictionary, right? Somewhere like right there. And you look at the words that like are on that page, and the words start with J on that page. If the words start with J on that page, that means that you flipped too far. So that means that you need to decrease your search window. So instead of our search window being the entire length of that dictionary, it becomes from halfway to the start. So Ashka, come like halfway here. Awesome. So then you flip to something that's like halfway between like the J page, where Ashka stands, and the beginning, where Simran stands. And that's like about over here, and the words start with like F on that page. So when you start with F, that also means that you're still too far, right? So then you need to like come back in again. Okay, so now you flip to a page halfway between the F page and the beginning, and the words start with B on that page. So here like things start with B, and you're just like, okay, wow, I came too far forward. So that means that I need to move my beginning to here. All right, cool. So now we have our ends at F and at B. So then you find something that's halfway between, and it starts with CE, and that's like right over here. It's super close. CE is still slightly too far forward. So now you go between CE, which is right here, and B. And you eventually get to CA, and you find on the page catalyst. So that's basically how binary search works. You're just decreasing your search window every time. Thank you. Yeah, thanks to all of our 2 great volunteers, right? Okay, so... Okay. So that's a really simple idea, right? So why is it that less than 10% of professional programmers are able to code a bug-free binary search? Like, I mean, a elementary schooler could get the idea behind it when you tell them to like searchable words in the dictionary, right? Why is it so hard? I think there's 3 main reasons, right? So we're going to talk about the code a little bit before we talk about the 3 main reasons. I don't expect you to memorize this code at all. I don't think that the right way to remember how to do binary searches is just by memorizing, like, okay, on line 1, we need to initialize our low, and then our high, and then, like, this while loop, like, all this other stuff. I do think that this is a good reference page that you should come back to eventually. But if you'll notice some important things about this code, the first is that you can write it iteratively or recursively. Most of the time, people find it easier to write it iteratively. At least that's the case with me. In addition to like just being like a bit easier to read and reason about, that everything's in one function, it also minimizes that recursive call stack space, right? In addition to that, you should notice that there are a lot of things that you could very easily get wrong. So, for example, like decreasing the length by 1 to make sure you don't go off the end of the array. Low is mid +1 here, and high is mid -1 over here. This one's less than, not less than, or equal to. You need to worry about integer division and how it truncates down in a lot of cases. And just a bunch of stuff, right? What exactly, like, do you, like, there are so many moving parts inside what many people consider to be a relatively simple function that, like, it's really important that you manage to get those edge cases down. And I think that's something that's, like, true to a lot of technical interviews. They will ask you something that like you can explain relatively easily, because it's really painful when you're sitting in a room with someone and they have like no idea how to even begin with a problem. They want to get to the point where the hard part comes out with the details and the implementation. That's why the first reason why binary search is so hard is because of off by 1 errors. Like, it's super hard to remember like whether to add 1, subtract 1, like whether it's less than or equal to or just less than, which exact variable you should be returning. My solution to that is to do, whenever you're doing binary search problems, and like you will see in a moment why you should do binary search problems, even though it's a very intuitive thing, try to code it the exact same way every single time. Try to make sure every single time you return mid, instead of like mixing it out and being like, oh, I should return like high -1 or something like that. The second reason is disguise problems. So not all binary search problems will initially seem like a binary search problem. We're going to look at a random number generator that will really hammer that home. I think another important thing to realize is that we talk about, like, so at Duke we combine data structures and algorithms for CompSci 201, right? But the two are fundamentally like there are certain algorithms that like work a lot better on certain data structures. But at the heart of it, what you're going to realize is that as interviews become harder and as more people memorize cracking the coding interview, they're going to start twisting problems in ways that are very like sneaky. right? You're going to have algorithms that don't seem to apply to that data structure at first, but you're going to have to do something to manipulate the input form in order to get the right output. And I think that that's a skill that you're going to learn, like you're going to have to learn throughout this class, especially as you like get into the challenge problems. So the final reason why binary search is so hard is because of what I call Icarus syndrome, right? Because it is so intuitive, like compared to like other things like, divide and conquer or like dynamic programming or whatnot. A lot of people will just say, okay, you know what? When time comes, I can code binary search. And then they start running into the edge issues, the infinite loops, the returning like one off the right value. Like the issues with like, like something, your target being at the very ends of your array instead of somewhere in the middle. It just ends up being, people just end up like overestimating what they're, like overestimating their own skill level. So pause right here. Everyone say hi to Gung. Gung's our 4th instructor.
Hey, guys.
Yeah. And he will be teaching, what's your first one? Trees? Yeah, we'll be teaching trees in about a month, so get familiar with his face. Awesome. So, okay, everyone read the problem description. I'm not going to read it out because y'all can read, and I'm going to give you like, 2 or 3 minutes to think about like how you might try to solve this problem. And if you're confident, feel free to come up. Otherwise, I'm going to have to select a random instructor, and I don't know if they want that.
If anyone else wants.
Yeah.
You gave us the answer. Feel free to collaborate.
Indeed, yeah, you can like whisper amongst yourselves. This isn't an interview. This is like.
Yeah, I guess. It's basically how do you say the name of this company?
Huh?
How do you say the name of this
Face Goog Soft Son. Any references to other entities, real or imagined, or purely coincidental? Yeah. Oh, also, if y'all haven't been noticing, all these lectures are recorded and they will be posted online to our Catalyst YouTube account. You'll have a link to that. A corollary of that is that let me know if you're not comfortable with, like, if you want to volunteer, but you're not comfortable like being recorded. We can try to work something out there.
True. The ideas. Is that figure real?
What? No, it's real. Like that's why I linked like a real article there.
Oh, it's true.
Yeah, I like. There's like a link at the bottom.
Did they do a control study or it was like a survey?
I think they just did a survey where it was like, yo, if you have like extra time, just like try to code our binary search and like we'll just like run it and see if it works.
Yeah.
All right.
I never saw it. You gotta show it to me.
Okay, so before we give away the answer, here's the way that our coding challenges are going to work. So I'm going to introduce a problem up here. I'm probably going to like talk about two like interviewing tactics before, like a couple of interviewing tactics beforehand, and then we're going to have a volunteer come up and we're going to code. And the way that we're going to code is literally I'm going to have you come up here and just feel free to take the stage. I will act as your fake interviewer. You can ask me any questions about the problem that you like, but you should treat it the way that you think that you would treat an actual interview. And remember, this is like a supportive community. Like we're all here just like try to help out each other. So even if you don't feel like 100% confident about the problem, or if you like haven't done an interview in years or like ever, it's totally fine. Feel free to come up and show us what you know. So given that, do we have any volunteers? Oscar.
Oscar, only if you let me do in Python.
Hey, it's not just me.
I don't think I have Python set up actually on this computer. I probably should. Yeah, but we want to have a test driver.
Oh, I can run it.
You're gonna run a test driver all by yourself? All right, cool.
Would you have Python installed?
I like it comes installed with every like
2.7?
OS X. Yeah. Do we have any other volunteers other than the president? Other than the president of the organization who is hosting this this thing? All right, sure, Brian, feel free. Okay. All right. All right. So, hey, welcome, Brian. Congrats.
Thank you, Bobby.
Congrats on making it to this stage. We were very impressed by your resume and all your relevant things. So, if you don't mind, we're just gonna jump right into the technicals. So. You've already read it. Just feel free. This is your time now. Just feel free to talk through how you do this.
Okay. Oh, should I do this like in an actual coding interview style?
Yeah, sure.
Okay.
Go for it.
So, are we making the assumption that is good just works automatically?
Yeah.
Okay. And here we have latest version. Okay. So the first thing I'm going to do is I know that most of the implementation is going to happen in this find last good version. And we're going to run this in a format of a binary search, like you explained to us earlier. So, latest version is...
Why are you doing this in a binary search?
Because we have a set of versions that we're looking through, and we know that the cost of running is very high. So we want to make the minimum number of checks of is good as is possible.
Mm-hmm.
And because we have a scale that says exactly how many versions that we have, which I'm assuming all of them are integer versions. And I'm assuming latest version is going to be the last version that was available. So we're going to run through it like that, and by dividing in half each time, we get the log n performance for it.
Okay, cool.
Okay, so I'm going to start with latest version, and the first thing I want to do is find the midpoint between the first version. Was it 1 or 0?
We'll say it's 1.
Okay. Okay, so the first thing we're going to want to find is the midpoint. So I'm going to start with int mid equals latest version divided by 2, and I'm going to want to cast that to an integer. Shoot, not using to the right click. Okay, so every single time, once we reach the midpoint, we're going to want to check whether or not it was a valid version number, if it was running or not. So we're going to find, we're going to create a Boolean. I'll store it in a Boolean for now. So equals is good, and we're going to run this using the mid. One sec. Okay, public static void.
Oh, sorry. That should be a Boolean, public static
Oh.
Boolean. Yeah.
Okay, so then I'm gonna see what happens when we reach this point. So if it works, that means that we need to go even earlier. If it doesn't work, it means we need to check versions from this midpoint up until the latest version. Oh, actually, one sec. So I might actually. Okay, I'm gonna actually do this and pull this out and create another method here. And
So while you're typing this up, you want to give me a high-level approach of how you're implementing binary
okay,
search?
so I'm assuming that find last good version is what we're going to be calling in our main to actually do this binary search. And what I'm doing here is I'm creating a helper method that takes in a low value and a high value, because sometimes, like if we have 10 versions and we find out that the 5th version is still working, then we know that the one that's not working is going to be in between 5 and 10. So I want to make sure that there is a low and a high that we can move in that range. What I was looking at earlier, the reason I'm doing this is because earlier we are only keeping one number in here. So when we run binary search, let's say it ends up, we're looking in the range 0 to 10 again, and let's say it ends up that we have number 5 working, then we don't have a low bounds, but we have a high bounds of 10. So I'm pulling this out as a helper method to make sure that we can keep track of both the lower bounds and the higher bounds. So this code I'm actually going to pull out and put into this helper method. And
so is this going to be a recursive method?
Yes, we're going to call this method recursively.
Okay.
And I'll deal with the base case in a sec. So right now we're looking at if our current value, which is our mid value, if it works. So if works, and then otherwise it doesn't work. So we have these two cases right now. If it is working, that means that whatever the mid value currently is was a valid version of the software. And since we need to figure out where it goes invalid, then we're going to have to, if it's working, we're going to update our lower bounds to be where mid was. So in that case, we're doing find last good version helper. And this is going to take our mid up until our high bounds. And then otherwise, we're going from our version 1 to our mid. Okay, so now we're going to be able to see what was the... Actually, I might actually introduce an additional variable here. Okay, so I'm going to keep an additional variable that keeps track of what the last working version was, because what we're looking for is the last version that was working before we start failing. So I'm going to say if, oh, actually I'll take this out at the bottom. So in this else statement, this is where we find that the current mid is not working. And if the current mid is not working, then we can go to... Oh, actually, that was not even necessary. I don't know what I'm doing here.
Okay.
Find low, high. Yeah, you know what? I'll finish the rest of the implementation first and then come back to that.
Okay.
So in our main... I'll just assume that there's some definition here, and then find last.
So I'm a bit confused as to how you're going to test this when like is good isn't defined yet. Like I said that I would give you is good, but like I think that this is one of those cases in which like it would be better for you to run through something just instead of like instead of compiling and running it, it might be better just to like logically run through what's going on.
Okay, so obviously this is totally incomplete, but what would ideally happen is you run the main program, which calls this find last good version, which is going to return an integer that is the last version that was working. And then in this helper method, which I might or might not introduce something else depending on when I finish thinking through this, but you start at a low and you go to a high value, and this is an implementation of binary search because we find the midpoint in between these low and the high values, and we figure out if it works. And if it's working, then we know that that midpoint is a working version. So the last working version is either the midpoint or something after the midpoint, in which case we run the lowest point is the midpoint, and the highest point is again whatever the previous highest point was.
Yeah.
And then otherwise, if the midpoint was not working, that means that the last working version comes before the midpoint, which would be which I would need to edit based on how I do this casting to remove the decimal there.
Okay.
Ultimately, you would need to return the last working version. So I guess I didn't really need that. Yeah, so when you reach a point where the low and the high, so that would be the base case. So if you reach a point where the low and the high are either exactly the same or they're spaced off by a very small amount, you figure out what's working in between the low and the high, and that's effectively your last working one. So what I'm going to write is if your low is equal to your high, and this is kind of inefficient here, but so if your low is equal to high and it is good, then you know that this is the latest working version.
Okay.
And then otherwise, there's a case where you could have low and high that are spaced apart by 1. And if it's what's that? And then if you have the low and high, actually technically they should always converge. Return mid, high, low, mid. Oh yeah, technically this is always going to converge. So actually that should work.
Okay. You might want to check your line 26 and line 33 a little bit.
Okay. 26. Oh. So this is going to be, we need the midpoint between the low and the high. So low plus high over 2 will give us the midpoint of those two. And line 33, find last good version. 1, 2, mid. You're starting at 1 and you reach your mid, but we're truncating off. So I think you need to add 1 here. Let me just double check that. Low plus high over 2.
So in this case, does low ever become anything except -1? Or instead of 1?
Low. Oh, there it is. Okay. So here's mid to high. So this is the case where you update low, and you lower high. So if it's working, you know that the range you should search for is from mid to high. And if it's not working, you know that the range you should be searching in is between 1. Actually, no, this should still be. But no, lows. Oh, here, you're right. This is an error location. So, this would be, I mean, there's a case, if we look at the base case, where your low and your high could both go to 1, so the first version of the software would not have been working, in which case it would, if it is working, it's going to return 1, and if it's not working, it's going to return 0. So for the case where there was never a version of working software, is it better to return 0 or -1?
I don't think that's the key issue here. Let me give you an example. All right. So let's say that I have versions from 1 to 7.
Okay.
And the last good version was 6.
Okay.
So can you run me through like how exactly this would go through?
Okay, so we have 1 for low and 7 for high.
Okay.
They're not equal, so this is all going to be ignored. And then we find the midpoint. So that's 1 plus 7, which is 8, divided by 2 is 4. So we're running is good on 4. So are we assuming that was working? Or oh, the last good version is 6. Okay, so 4 is working, in which case it works. So we start our search at 4 and we end it at 7. So now we go back through the top of the loop running 4 and 7. They're not equivalent, so we go over here. 4 plus 7 is equal to 11. And then 11 divided by 2 is 5.5, but it's going to truncate to 5. 5 is working. So we go to works, and we're running 5 to 7. We again skip through low equals high. 5 plus 7 is 12. 12 divided by 2 is equal to 6. And then we run Boolean works, and we get true, it is working. So it is working. So here we start at our midpoint 6, and we end at our high point of 7. Now we have 6 and 7 here. They're not equivalent. We run through again. 6 plus 7 is 13. 13 over 2 is 6.5. Truncating the decimal again, and we end up with 6 again. So there would need to be, this would cause an effectively 6, if it is good. Yeah, so this would go back over here, 6 and 7. So in that case, there's a loop here that's going to keep on looping, because 6 plus 7 is always going to be 13, and we're always going to end up with 6 as the mid. So if, actually I might run this computation in the beginning. If low is equal to mid, actually maybe I'll still do this here. If low is equal to mid,
Okay, so I think that you have a couple of off by 1 errors that can be resolved relatively soon. But I think there's still one key error that will cause this binary search to not converge to correct values. Even disregarding infinite loops and off by 1 errors. Like, let's try to figure that out, and then let's move on to another problem.
Okay.
I told you to check out line 44 before. What do you think is the issue there?
So line 44 is going to run the helper method in between 1, which is the earliest version possible, against the mid, and this is
So why is it 1 there instead of being like low? Like, isn't that how binary search normally
Oh
works?
shoot. Okay, so and we're going to, let me actually see for that. Mid.
Okay, so for the most part, like we've gotten the basics of binary search down. I'll upload solutions I'll upload solutions after class for this. But I think that there was a key insight which is necessary here, which is that you actually need to compare something that, so it's possible to do it. It might be possible the way to do it the way that you're doing it. But if you had like an array of like bad, 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 good, good, good,
Mhm.
or like, let's just do it this way, right? Or let's just use this practice array. So eventually you're going to need to be at a point where like you realize that there's a separate way for you to handle like ending up in a good where the previous one is good and a good where the previous one is bad. And I think that you were like at the beginnings of trying to figure that out, but like that's like pretty important.
Mhm.
In addition, normally we change the bounds of binary search by one, so that way like when we say that like our mid is currently like not the element that we're looking for line 44 we'd say like then we're going to look between mid plus 1 and high, and over here we're going to say we're looking between mid minus 1
Okay.
and low, and that way you can make sure that you don't get into the infinite loop. This was like not a super easy problem because it's not just binary search, it's binary search with a couple of twists, right? But I think that what we were trying to get into, in addition to that, was that you need to be able to like not only write out the code, but also to be able to reason about the code and explain it to your interviewer. And I think you did a relatively good job at that. So let's go back to the interviewing tactics. Yeah.
Can we do it iteratively?
Yeah. So also, I think that like just in my personal experience, you will make a lot fewer mistakes writing it iteratively. For a couple of reasons. So first, like most people tend to think iteratively rather than recursively, and second, you can use print statements a lot more effectively when you're iterating versus like when you're recursing. Because like in a lot of cases, especially as you go into harder like problems that could be written recursively, you don't even know what level of recursion you're at when you're doing certain print statements. And chances are the IDE that you're coding in won't have a debugger, so you won't be able to like go through the call stack either. Yeah.
So about the algorithm for that particular question.
Yeah.
The way that you would kind of like figure out whether you're like next to a bad or good, or next to something that's opposite you,
Yeah.
which is like where you want to be.
Yeah.
Would you, I guess, in my head I'm thinking that you can either do that one of two ways, which is like whenever you get to a new mid, check what's before you, but that's terrible because you have to do is good for
Yeah.
every single step.
Mhm.
Or else you can just kind of like, I guess, whenever the difference between where you like moved from, like old mid to new mid, is 1, then you know that you went to like a place where they back and forth. So
Yeah.
is that correct?
So that's one way of doing it. Another way of doing it is making sure that you only, so like if you converge such that like you only get to low equals high when like this is right on the border, then you're good. There's a couple of ways of doing it. Another way of doing it would be to prevent like multiple computations of the same number. You could say, okay, I'm going to use a hash map to store like whether each like int I over here is like good or not. As you like iteratively like go through the array and like decrease your window there. Yeah.
Can I try the iterative way?
Can you try the iterative way? Ooh, we are a bit short on time, but
Are we really gonna get through all problems?
I think that it's important for us to like go through a greater variety of problems. Yeah, especially when we can like give the working code after class.
I also wanted to point out like some good like just general strategies that like you could see when they were doing like the mock interview. So the first thing he asked you like kind of clarifying questions, so you always want to do that. And it's kind of intuitive when you're like later in the process, but like when you're starting, don't just like jump into a coding solution. And then something else that I learned from Bobby, like when he was like helping me out when I was interviewing, was like don't zone out when you're like thinking, because like it's really easy to like when like Bobby asked him a question, like you kind of zone out, but then you like start talking again. So it's okay to like stop a little bit, but try to keep like speaking about your thought process just to make sure like everyone's on the same page. But those are kind of like material, like not material specific, so just like general.
Yeah. The reason why we do these like sort of like live interview things is because there are so many nuances to like actual interview strategy in addition to the comp sci like preliminaries that I don't think you can really get like a full course unless you see a bunch of interviews in action, which is why like I really appreciate when y'all like volunteer and come up, because otherwise like we wouldn't be able to point out these small things that like we might not even notice that we're doing, but which like become very apparent towards a larger audience. Oscar, do you say something?
I was just going to say, in terms of binary search, if you want to do it the iterative way, it's almost always like if, else, And if you think about it, like when they were doing that thing at the front, it's almost always you're too far, or you're not far enough, or you're just right. Right? So think about what those three conditions would be. And in this case, like exactly what you said, right? If you're too far, then the case would be the one before. The one before is, can you go back to your example?
Yeah.
If you're right, so if you're too far, then the one before is good and you're good. Right? The one you're on is good. If you're not far enough, then you're bad, and the one after you is also bad, right? But you're just right if you're bad, and the next one is good. So if you just think about those three conditions, and if you look at the previous slide for binary search, it's almost always like the three conditions.
Yeah, so here was the code that I wrote when I was like trying to like prove like this class, or like when I was practicing a lecture for this class, and it was an iterative version, but just like Oscar said, there is an if else statement, right? And so over here, this first if statement is a condition that you're like just on the edge. The second else if statement is that like you are not far enough or too far, and this third else statement is that like you aren't far enough. And
I would to write it out in Princeton.
Yeah. So I was hoping to get into testing, but luckily we have an entire semester to get more into testing. But it's often useful for you to like write your own test suite in some way. So you can see the beginnings of that in this method over here, where you like basically just like initialize your own like fake like is good array or whatever, and then try to test it on that. So there's that. Okay, so here are three interviewing tactics that I hope that you saw something of in regards to that first question, right? So the first is like even if your interviewer doesn't prompt you, try to figure out ways that you can like test your code. It really impresses interviewers when you can like modularize your code and make sure that it works out like even the smallest step. The second one is language familiarity. So I don't know if I pulled a fast one on you, but there's just certain things like knowing that like in Java, like integer division always rounds down, so you don't need to like cast to an int, or like knowing about certain things like, oh, you need to have the static keyword in order for you to like run a method inside that same class, you like in your main method. And the third one is talking it through, and that's something that Brian did a really good job of. Like there was never a point in time in which like I wasn't very cognizant of like what was going on in his mind, because like even if you aren't exactly right, you can still get in many cases like significant partial credit or whatever you want to call it in the eyes of your interviewer by just like stating your thoughts. So thank you very much for that, and everyone give him a round of applause for volunteering. Awesome. So the way that's going to happen is we have like about 20 minutes left, which I don't think is we're able to get through like both of the problems after this. So instead of going through with like full coding, let's just talk about like what the solution might be and how it can be a twist on binary search. Afterwards, I will post the solutions, and if y'all have any questions, then you can like email me or the other instructors about clarification. But we are running a bit short on time, so let's jump into the next problem. Okay, this one's called peak performance. Feel free to read through it, and then in about 5 minutes, like talk to your neighbors about it. In about 5 minutes, let's reconvene and talk about how we can solve this problem. Is this a question or a possible solution? Okay, yeah.
Are we allowed to put the telescope at the very ends of, I guess, the world?
Yeah, great question. So these are sorts of questions that you should be asking your interviewer. Say that you have an ever-increasing slope. In that case, you may put the telescope anywhere. You may put the telescope anywhere, but it might be easier for you to put it at the end. Yeah.
What if you have only one or two things in your array? Do you need a
Yeah, so another great question. Like, what happens if the array only has, like, one element? Or no elements, or just two elements, right? In that case, you should return... you should return the first element if the first element exists of the array. If the array is of length 0, then just return 0. And just to be clear, when you're returning the peak, you should return the index of that peak. Yeah.
Which means that if there's nothing, we should return -1 because 0 is an index.
Yeah, fair. Again, it's very good that y'all are asking about these edge cases, because like it's really just up to the discretion of the interviewer, like what you want to return. Like, I mean, I could have said like, yo, if there's like no peak, return like integer, like java.lang.integer.max value. Like that's also totally valid. I think an example might be helpful. Okay.
Wow, you zoom into like one day or half a day and it's just always going down.
Yeah. Yeah.
Edge case.
Okay, so let's just get someone up and just talk through it, and we'll figure out how to code it later. Does anybody want to explain their idea? It probably might help for you to like actually point to stuff on this thing. So note that in this case, you could find several quote-unquote peaks, right? There's this peak that you could find, this peak, this peak, this peak, this peak. There's no need to find a global maximum, only a local one. Yeah, sure. Do you want to come up and like, yeah, point to stuff?
So like I've just thought about this a lot. Like it's just an idea.
Uh-huh.
But like since we have like the 3 points, right?
Yeah.
So we could find whether it's increasing or decreasing.
Yeah.
So like if it's increasing, it would mean we would be going like up the hill, right?
Mm-hmm.
And so if we find that it's increasing, we could find like a point between there and the end, because like let's say like the whole thing is increasing.
Uh-huh.
And then if it's decreasing, then we limit it there and go the other way.
Yeah, so that's totally fair. That's pretty much the algorithm in a nutshell. So if we had like this, for example, then we would start off and we would go over here and we'd say, okay, here it's increasing, which means that we know for sure that there will exist some peak over here, or it'll just end up being like an endpoint. And the reason why is because either it will continue increasing or at some point it must decrease, right? So you say, okay, cool, I'm over here. That means that I need to go further over here, and I'm going to look at another half point. So then you say, okay, I'm going to look over here, and here it's decreasing in this direction. It's increasing in this direction. So you need to look at the half point between like here and here, which means that you go to here, right? And so, you go to over here. And at this point, you're like, okay, well, it's still decreasing, which means that if there is a peak, it would be somewhere in the middle, and it would just keep iteratively decreasing until you found like one of the peaks over here. So that's the general idea. This is a bit harder because you do have to deal with the whole thing about like your binary search condition being slightly different. Instead of something being exactly equal, you need to think about like the quote unquote slope of whatever it is that you're going through. So, thank you. All right. Okay. So we have time for one last thing to sort of like, just think about. And okay, so if we were to do this like fully, then we would try to take a look at like the second set of interviewing tactics, right? So the first one is like twisting the problem, in that a lot of the problems that you see are going to be like subtle twists on it. This one was more twisted than the one that we saw like in the very beginning, where like is good was basically just binary search. This one had to like involve like a bit more thinking about like slopes, and like you might even start to think about like a calculus based version where you like use like gradient ascent, like all that other stuff. But in general, like as more people try to get tech jobs, like interview problems will get harder. The concepts won't, but the implementation will. And the way that they make the implementation harder is like they have some preliminaries that require you to like twist the problem in a certain way. So the second thing that you need to worry about is like attention to detail, right? Where we were dealing with an array of doubles, but like we're still indexing based off of like integers, and like it just generally makes sense for you to like always make sure that your variable types are what you think they are, especially if you're using a language like Python, where it won't even give you a compiler error if your types don't exactly match up. So just more food for thought. Okay, all right, here's the final problem. And this is also another thing that I recommend for this class. Like, we have a bunch of like beautiful desks here that can actually support like real writing. There's gonna, especially when we get into like the more like graphical data structures, like trees and graphs, like it'll be very hard for you to like. It'll be much harder for you to keep up with the course if you don't like actually draw things out on paper. I think this is one of those where like it definitely helps to write out some numbers. Yeah. Yeah, this is a binary search problem. Wait, G, do you remember how to do this problem?
This was the one.
How would you get
Yeah, this was the one that I gave you a while back.
I create another array.
Do you have any recollection of like the solution,
In which
or
case you iterate through and add cumulative. So like the first number will be 1/6, and the second number will be 1/3, all the way until the thing.
yeah?
Then
Question?
What's the rand function like?
It's just given to you. Like, just consider it like you know how like Java has like a random like.
What is it supposed to be doing in this question?
So like, I want you to basically convert a call of the rand function into a generating an integer based off of the probability distribution function given by that array of doubles. So for example, if I gave you this, then if I called generate 10 times, then like using a call of the rand function every single time I call generate, it should, or say I call it like 1,000 times. This should have about 100. This should have about 200. This should have about 300. This should have about 400.
Was it generate basically all random?
Yeah, but generates a random function that like is uniform, or it generates a random number that's uniform between 0 and 1. We want to be able to use that as a building block. Yeah, math.random generates like just a uniformly random number between 0 and 1. We want to be able to extend that and use that as a building block such that if we were also given this probability distribution function, we can return a integer with that specific probability.
So like I don't see like the connection between random and the rest of the question. Isn't generate just finding an integer based on the probability function?
Yeah, so how would you randomly generate an integer then?
Isn't it based on the probability estimate function?
Yeah, but what would you use as like the basis of that randomness? Yeah. I can't just say like return 10 ones in a row and like 22s in a row and so on. Yeah.
Oh, can I give a solution?
Yeah, sure. Feel free.
So you create another double array that's the same length as the PDF array that you get in, and in this double array, you're gonna do an iterative for loop and put in the cumulative probabilities up until that point for each of them. So you get 1/6, 2/6, 3/6, 4/6, 5/6, 6/6.
Yeah.
Then you run math.rand and search for the value that you get from math.rand in that array, and when it's in between two values, then you just return the higher index.
Yeah, that sounds pretty valid. So just to visualize what Brian was talking about, say that this is what we have, right? So we have like, we'll call this like 0, 1, 2, 3, 4, right?
I think you should adjust to the probabilities to be like 0.1.
Oh, yeah. Okay. Okay, so that's fair. So let's say that we have like, wait, does that add up? Does that? Okay, yeah. So this is our PDF, right? We want to turn this into a cumulative distributive function. That is, we add everything to it beforehand too. So we have a 0.2, 0.5, 0.6, 0.8, and 1. And then say that we generate a random number. If we were to do this linearly, because every binary search problem can be done linearly, like binary search is just a faster way to do linear search. Let's say that we generate a number that's 0.7, right? Okay, so, or let's say 0.9. So in that case, like we'd have our highs and lows. We'd have our high and lows start off over here, right? And you say, okay, so we have 0.2 and we have 1, and then the average between those two. Okay, so we have our stuff at 0, we have our low at 0, and we have our high at 4. The average between those two is 2, and we say, okay, so we're at 2. That's 0.6. 0.6 And okay, so we look at 0.6 and the number immediately preceding it, because implicitly we have a 0 like before the start of our array, right? But we don't write that in because it's a cumulative distributive function. At that point we say, okay, so we have 0.6 and 0.5. Is our number between 0.6 and 0.5? No? All right, well, our new low is now 2. Then we do binary search again. Mid is 3. And we say, okay, so mid is now 3, and we want to do, we want to see whether our thing is between 0.6 and 0.8. No? All right, well, our new low is now 3. So now we take a look and we say, okay, so we're going to our new low is now 4. And when we take a look at our new low of being 4 over here, we say okay, so our low is equal to our high, which is equal to our mid. And we take a look and we say, okay, is our thing between the range of 0.8 and 1? Yes. All right, cool. Output of 4. And that's how you partition the line from 0 to 1 into like any number of integers based off of a given probability function distribution. Yeah.
Oh, sorry, when it's in between, do you always choose the middle one?
Yeah, so you can choose to have, this is like a based off the taste of your implementation, right? If you chose to start your array at 0 and then go to 0.2 and then 0.5 and so on and so forth, then you would go to the lower number. But you always go to the higher number because you can't max out at like a random number higher than 1. Yeah.
Like a quick tip, if you go into an interview and you see an interview question that you don't understand, even after the interviewer has given you an example, ask for more examples.
Yeah.
So usually it's like spacing out, right? Like just keep asking questions and clarifying the problem. Even if it seems at the start like you don't really know what's going on, or like he mentioned something that you've never seen before. Like it makes 100% sense to just ask him what it is and not like try to pretend like you might know it. And that's definitely valid. Like that's so much better than just not saying anything or like trying to fumble around.
Yeah, absolutely. So this was a real interview question. I don't think I got it until I got like a bunch of examples. Like he started off with just like a fair coin example, and I was like, wait, this tells me nothing. Until eventually I got this specific example, and then I was like, oh, okay, it's starting to make more sense now. This goes back to the whole thing about how you should always try to tease your interviewer for more information, because like at the end of the day, they are the ones who are like assessing you, and you want to do things according to like their specifications. So interviewing tactics 3, right? So the trade-offs. So there's a trade-off, just like I talked about like before, where in order for us to implement Brian's solution, we needed to implement an auxiliary array of like a cumulative distributive function. If we were allowed to change the input, which you should always ask your interviewer whether you're allowed to change the input, then you could do it with no extra space. But in many cases, you'll have to like have some sort of a space-time trade-off. The other thing this would have been more relevant is helper methods. For example, I would have written like a range checker helper method to see if a number fell within like a certain 2 like array indices, so that way you can like keep the remainder of your code clean. So I'm gonna finish off by a word of warning about when not to use binary search, right? So it seems like, wow, binary search can be used in a lot of cases where it's really hard to even visualize binary search being used, but there's other cases where it seems obvious, but you actually can't use binary search. For example, when element access isn't like constant time. So if you have a sorted linked list, you should not binary search that, since accessing any element in the middle of a linked list is not going to be a constant time operation. We'll talk more about that when we get into linked lists themselves. So like, as a result of that, like just always make sure that you have the preliminaries of like binary search usually being on some sort of array or other thing where you can have like O of 1 access. The second thing not to use binary search on is multi-dimensional arrays. If you try to do a binary search on like a column and row-wise sorted matrix, you're going to have a bad time. It will not converge to a correct solution. All right. So thank you all for coming. If you have any questions, just let any of the instructors know. We'll be back here next week. I'll stick around for a while afterwards too if you have any questions about the material today.
And please pick up a fast